I would like to welcome back all of you to the last 2 weeks of the solar energy course. So far, you have seen the basic principles of semiconductor-based solar cells, the operation and design of solar cells, the various PV technologies, solar thermal concepts, and even novel state-of-the-art concepts like solar fuels. In this video, I will briefly explain what to expect from the last 2 weeks of this course. In these last 2 weeks, we shall focus on the more commonly known field in photovoltaics, PV systems. First, let us look at a typical PV system. Here, I show a grid-connected PV system. The grid-connected topology is especially very common in countries that have supporting solar policies where excess power generated by the consumer can be fed back to the electric grid. In this case, a set of PV panels are responsible for power generation. The PV generated power is not only able to meet the load requirements, but is also able to feed the excess power generated to the electric grid when the supply exceeds the load demand. Let's look at such a system in action in the following 3D illustration. On a normal day, with the sun out, the PV modules on top of this rooftop are busy converting the incoming irradiance into photo-generated power. The grid-connected solar inverters used in the system are also constantly converting the DC output of the solar module into usable AC power. The PV system is able to meet the load demand of the household. On a different day, if it's a very sunny day, the PV system is providing much higher power than what the load needs. Under such a condition, the excess power is fed to the grid. In most countries, the consumer can offset his electric bills in this manner. This facility is called net metering. Even after a solar cell has been designed perfectly using the concept you learned in the first 6 weeks, there are still many other factors that contribute to the working of a good PV system. In week 7, we shall look at the various system components and their properties. In week 8, we shall look at how these components come together and function as a system that are widely in use today. What do we mean by PV system components? Let's look at this figure, for instance. Here, a typical off-grid or standalone PV system is shown. Different components that constitute this PV system can be seen. The PV system uses a PV module or a bunch of modules interconnected to form an array. PV modules, although just an interconnection of solar cells, have a different set of design and operational constraints when being used in a PV system. Is it just enough that we place the PV modules randomly on the rooftop? Do harsh summer and winter conditions have any impact on the PV output? We shall learn more about all these in the next block. You can also see a battery that is responsible for storing the excess energy. The stored energy can be used when the PV generated power is not enough to meet the load demand. In order to ensure the electrical specifications of the battery are being respected by the rest of the circuit, a charge controller is used. An inverter is used to convert the DC power into usable AC power for the required application. All these PV system components and important concepts like maximum power point tracking will be discussed this week. By putting together these components, we can get different topologies for PV systems. The main features of designing such system shall be discussed in week 8, the last week of this course. What makes a standalone PV system different from a grid-connected one? Which system topology is a better choice for a particular application? and how do we go about designing a PV system for a specific application? These are some of the main questions that I will answer in the last week of the course. I would also cover in the final week the economics and the environmental aspects of the PV system. A lot of people complain that going solar is not cheap enough, or that rooftop PV doesn't pay back in its lifetime the money invested in the system. We shall examine these claims on the economics of PV systems with an unbiased, objective approach. I shall introduce you to the basic terms like the payback period and the levelized cost of electricity. At the end of the final week, you would hopefully be in a position to perform basic calculations and see for yourself as to which factors would make the economics of a PV system more favorable. Lastly, I would also include in brief an interesting topic in week 8, that of the energy payback time. A lot of people believe in the myth that solar panels consume more power in the manufacture process than they would ever produce in their lifetime. Is this really true? If it were, I would not be standing here advocating solar power. But how do the numbers actually compare? That is something we will see in the final week of this course. So, are you ready for the last and the most interesting 2 weeks of this course? Then, see you back in the next block. Welcome back. In this block, we shall focus on the central character of the PV system, the PV modules. Before I start, I want to touch upon briefly on the subtle difference between the terms solar modules and solar panels. You must have observed that a lot of people use these terms interchangeably, but what is exact the difference? A module is an interconnection of solar cells, as you had seen before. It is the generic name given to any kind of packaging for an interconnection of solar cells. That is, irrespective of technology or packaging, an interconnection of solar cells will be called a module. However, the term solar panel is a bit more exclusive for the rectangular, rigid packaging with typical encapsulations. For example, most standard crystalline modules are called solar panels. All solar panels are solar modules, but the converse is not true. For instance, a thin film silicon solar cell that is packaged as a flexible laminate is a solar module, but it's not entirely accurate to call it a panel. Note that in most cases the commercial modules being used are panels, and therefore modules are synonymously called as panels in common usage. Henceforth, I might use the term solar panels and modules interchangeably as well, but I hope you understand the exact difference between the two. So let us move on to the module level concepts. First of all, I would like to introduce a new term, the IV curve. So far we have been discussing the JV curve at the solar cell level, J being the current density, current per unit area. But at the module level, the total current that the module can generate is of more interest. Hence, we look at an IV curve, or the current voltage curve. As the area is a constant, the IV and JV curve of the solar cell or solar module will have identical nature. As a quick recap, you might remember how a solar module exhibits similar output characteristic to a solar cell, as a module is nothing but an interconnection of solar cells. In a nutshell, it can be said that just like for the solar cells, a set of parameters can be similarly defined for the solar modules, like module efficiency, module fill factor, the open circuit voltage, and the short circuit current can be defined. You will remember that the voltage and current characteristic for a module with M identical cells in series and N identical cells in parallel will look like this. The current multiplies by a factor of n due to parallel connection, and the voltage multiplies by a factor m due to a series connection. But what about the other parameters like efficiency and fill factor for a solar module? Do they increase, decrease, or stay the same? Think about this for a moment. In an ideal world with perfectly matched solar cells and no losses, one would expect that the efficiency and the fill factor at both the module and cell levels to be the same. But this is not the case in practice. We know that cells are connected together using interconnects. Although a very small amount resistive losses occur in these interconnects. Also, there might be a small mismatch in the cells that are interconnected. For instance, of the M times N cells interconnected, the cell with the lowest current in the M cells in series dictates the module current. Similarly, the cell with the lowest voltage in the N cells in parallel dictates the module voltage. This can be attributed to the non-homogeneity of the cells in mass production. Therefore, the module in practice performs a little subpar compared to the expected performance of the ideally matched and interconnected solar cells. This translates to a lower fill factor and efficiency at the module level. In fact, if the module is undergoing variable illumination or non-uniform heating, the module performance is bound to get even worse. Even module manufacturers mention in their data sheets the difference between module and cell efficiency. For example, the data sheet of a Sanyo HIT N240SE10 module speaks of a cell efficiency of 21.6%, but a module level efficiency of 90%. Perhaps this gives you an idea of how different the cell and module level parameters can be. Even though so many technological advancements are being made at the cell level to improve efficiency, as discussed in the previous weeks, there is still a lot to be done at the PV system level to ensure a healthy PV yield. Getting a good module in terms of efficiency and output sensitivity is winning only half the battle. What matters ultimately is the yield of the PV system. So the question is, what else can you do to increase the yield of your PV system at the system level? Of course, maximum power point tracking is a valuable tool to ensure that the PV module always operates at the maximum power point on an IV curve, under a given set of irradiance and temperature. This will be discussed in great detail in block 7.3, dedicated to maximum power point tracking. But how do we improve the amount of light falling on the PV module at the system level? The simplest way of doing that is by playing with the orientation and tilt of the module. What do we mean by orientation and tilt? Tilt is the degree of freedom that defines the elevation or the pitch of the solar module with respect to the horizontal. Orientation is the degree of freedom that defines the azimuth or the yaw of the module with respect to a position which, in this case, is the geographic south. Note that the different places and people have different practices of defining the azimuth. The most common reference points are the geographic north and south. So how does playing with the orientation and tilt of the PV module alter the amount of light falling on it? For this, let's take a look at this animation. As seen in this video, there is a solar panel tracking the sun by varying the tilt and orientation continuously. Of course, this stems from the basic fact that in order to get maximum energy from the sun at any instant, The plane of the solar panel, or the plane of array as sometimes called, should be perpendicular to the direct rays of the sun at that instant. The amount of solar energy falling on the Earth is dependent on astronomical factors like the tilt of the Earth's axis and the near spherical shape of the Earth. These factors combined with celestial mechanics give rise to the complex path vector between the Sun and the point of the surface of the Earth. As a result, we see the need for having to track the Sun by changing the tilt and orientation of the solar modules. Let's try to study this a little more. Why do we need to change the orientation of the solar panels to always face the Sun? This is because of the Earth's rotation. Here you see how the Earth is rotating on its own axis, which is inclined 23.5 degrees to the perpendicular to the plane of the Earth's orbit. As the Earth rotates, different places on the surface of the Earth are illuminated differently at various points of time during the day. Thus, the need for solar panels orientations arises. In this animation, it is seen clearly how the solar panel is changing its orientation during the day. Simple orientation need not be a result of complex calculations though. Common sense dictates that a place in the northern hemisphere will have the solar panels facing in general direction of south, while a place in the southern hemisphere will have the solar panels facing in the general direction of north. Now, why do we need to change the tilt as well? This is because the Earth is revolving around the Sun in an elliptical orbit as shown. While the 23.5 degree inclination of the Earth remains the same with respect to the Earth's orbital plane, the Earth's axis is continuously changing position relative to the Sun's rays. Now, this complicates the relative path between the Sun and the Earth even more. The existence of the various seasons is also because of this very reason. Its effect is that in June and December, the Sun is closer to the northern and southern hemispheres, mid-latitudes respectively, while in March and September it's closer to the equator. Thus we see a need to vary the tilt of the solar panel. This is exactly what is shown in the video, that the tilt of the solar panel is changing as the year progresses. Now, most solar panels or systems don't have the luxury of employing a dual-axis solar tracker. Not only are they very expensive, they are also difficult to implement if the panels are to be mounted on the rooftop. Hence, the need arises for the concept of an optimized orientation and tilt. What do I mean by this? As the majority of PV systems have fixed mounting of panels, designers have to live with a single orientation and tilt throughout the year. So what should these fixed angles be? The answer would change depending on the geographical location. Here we see various places marked along with their latitudes on the globe. Depending on the latitude of the place, a panel tracking the Sun will have to go through a range of tilt angles throughout the year. Let's see how a Sun tracking PV panel is working in different places around the Earth. We will first go to London. London has a latitude of around 51 degrees. Consequently, the range of tilt angles throughout the year for a panel tracking the Sun varies from 28 degrees to 76 degrees. The panel in this case is oriented towards the south. The optimized angle of tilt will be 35 up to 40 degrees facing south. Moving closer to the equator, we have Cairo at around 30 degrees latitude. We notice that the range of tilt angles has diminished to around 6 to 54 degrees. The optimized angle of tilt in such a case would be around 20 up to 25 degrees facing south. Now let's go to the southern hemisphere with a solar panel mounted in Sydney. Sydney has a latitude of around 34 degrees. Note that being in the southern hemisphere, the panel is oriented towards the north. We see that the range of tilts experienced by the PV panel is from 10 degrees to 58 degrees. The optimized angle of tilt in such a case would be around 30 degrees facing north. It has been seen in practice that optimized angles can give up to 70 to 80% of the maximum PV yield. As long as the solar panels are facing in the right direction in general, that is, facing south for a panel in the northern hemisphere and north for a panel in the southern hemisphere, it's usually observed that the variation in the optimal orientation angle doesn't vary the PV yield much. Consequently, the optimal tilt of the panels help in saving more energy than the optimal orientation. It is also interesting to note that the optimized tilt could also be based on the seasons. That is, we could either use an angle that maximizes the PV yield in summer or in winter. This could be interesting for application-specific PV systems. Thus, we have seen the importance of the orientation and tilt for the PV module. Now, we have one more important effect to discuss at the module level, and that is the temperature effect. I will discuss that in the next video. Welcome back. So far, we have seen the important aspects to be taken into account while dealing with modules at the PV system level. We also know that irradiance has an effect on the output of the PV module. In general, all other parameters being unchanged, higher the irradiance, greater the output power generated. In this block, I would like to discuss with you the effect of a parameter of great importance, the temperature. First, I would like to answer the simple question, is a greater temperature better for the PV output, or is PV output independent of the temperature changes? In this graph, you see the IV curve of a PV module at a given irradiance and temperature. Now, if the temperature increases while the irradiance is constant, we see an IV curve that looks like this. So we see that while the current has very minorly increased, there is a significant drop in voltage. This means that the overall power output has decreased. On the other hand, if the temperature were to decrease with respect to the original conditions, while the irradiance were constant, the PV output would show an increase. The minor increase in current with temperature can be explained with the fact that carrier concentration and mobility increase in the semiconductor with temperature. This is consistent with our basic understanding that a semiconductor, unlike a regular conductor, exhibits better conductivity with increasing temperature and is a perfect insulator at absolute temperature of 0 Kelvin. The decreasing effect on voltage can be explained from this form of the basic diode equation seen in the earlier weeks. While the temperature affects the various terms in the equation, the net effect of temperature is that it decreases the open circuit voltage linearly. The drop in open circuit voltage with temperature is mainly related to the increase in the leakage currents of the photodiode I0 in the dark with temperature. The I0 strongly depends on the temperature. We have dedicated one of the exercises this week to this effect. The magnitude of reduction varies inversely with the open circuit voltage. This means that cells with higher open circuit voltage are less affected by the temperature than cells with lower open circuit voltage. This means that a solar cell based on crystalline silicon with an open circuit voltage of 650 millivolts will be more affected than an amorphous silicon solar cell with an open circuit voltage of 850 millivolts. So now you have an idea of the effect of temperature on the PV output. But how do we quantify this effect? If the temperature of the PV module were to increase by 10 degrees Celsius, how would the output be affected? Well, the PV module manufacturers include what are known as the temperature coefficients in the datasheets of the commercial modules. Temperature coefficient is nothing but the rate of change of a parameter with a temperature. For instance, the temperature coefficient of voltage is the rate of change of the voltage with temperature. Similarly, temperature coefficient of power is the rate of change of the output power with temperature. A typical datasheet of a commercial PV module specifies temperature coefficients for the power, the open circuit voltage, and the short circuit current under standard test conditions. Given these coefficients, how do we calculate the PV output with respect to the temperature change? We can use this simple equation. The term dx dt denotes the temperature coefficient of the particular parameter. The reference temperature taken for this calculation is the standard test condition temperature, which is 25 degrees Celsius. Let's take a look at an example. If the maximum power output of a PV module under standard test conditions is 250 watts, and the temperature coefficient of power is -2 watts per degree Celsius, then the module's power output at a temperature of 30 degrees Celsius can be calculated as follows. The power is 250 watts plus -2 watts per degree multiplied by the temperature difference 30 minus 25 degrees Celsius, which gives you 240 watts. As you can see, the sign of the temperature coefficient determines if the parameter is increasing or decreasing with temperature. In the exercises for this block, you will be able to use this equation to estimate the effect of temperature on the various PV parameters. Now, we must be careful while making these calculations. In the previous example, when we said that the temperature was 30 degrees Celsius, did we mean the PV module's temperature or the ambient temperature? Should the two be the same? As it turns out, the module temperature or the cell temperature, the popular term in literature, can be quite different from the ambient temperature. Let's see why there should be a difference between the module temperature and the ambient temperature. There could be several factors impacting the heat flow in and out of modules. Encapsulation of the solar cells is a major factor in increasing the operating temperature of the PV module. The eventual operating temperature of a module will be a result of the thermal equilibrium between the heat generated by the PV module, the heat lost to the surrounding environment. The heat exchange with the environment in turn could depend on several factors like ambient temperature, wind, heat transfer coefficients between the module and the environment, and the thermal conductivity of the module's body. Then, how do we estimate the module temperature based on the ambient temperature if we have to account for so many factors? Fortunately, there is a model provided in literature that gives a reasonable estimate of the module temperature as a function of the ambient temperature. This model is sometimes called the NOCT model due to the use of the nominal operating cell temperature or NOCT of the PV cell or module. The NOCT is a parameter defined for a particular PV module. NOCT is the temperature attained by the PV cell under an irradiance of 800 watts per square meters with a nominal wind speed of 1 meter per second and an ambient temperature of 20 degrees Celsius. Here, G is the irradiance at the instant when the ambient temperature is T ambient. The model gives the corresponding cell temperature as T cell. As can be seen from this equation, the cell temperature is not only a function of the ambient temperature, but also of the irradiance. This makes things interesting, because if we consider the irradiance and temperature changes over a calendar year, we would see an effect of both irradiance and temperature across the seasons. This can be seen in the graph shown, which has been made using the actual ambient temperature and irradiance data as seen in the Netherlands in the year 2012. The corresponding cell temperatures have been calculated using the NOCT model. This graph outlines the main inferences from the NOCT model. The line indicates the cell temperature is ambient temperature line. There are no data values below this line as there are no negative irradiance values. This means that the cell temperature can never go below the ambient temperature. The least cell temperature values will be equal to the corresponding ambient temperature, and these will occur when there is zero irradiance, in other words, at night. The uneven spread of the cell temperature above the ambient temperature can also be explained. When the cell temperature is closer to the ambient temperature, this is because the impact of irradiance is lesser, meaning these set of points correspond to the irradiance and ambient temperatures during winter. Similarly, when the T cell values go much higher than the ambient values, it's because the irradiance effect in the summer is quite high. This gives us some fascinating insights. This means that in summer, although the sun is shining more, the module is performing worse due to the temperature effects that bring down the PV output at a high cell temperature. In winter, the detrimental temperature effects are far less, although the irradiance levels also fall severely in winter. This means that the best ambient conditions for your PV module would be a cold day with plenty of sun. So how serious can this temperature effect be for a PV module's output over the calendar year? At the PVMD group of the Delft University of Technology, we have done an extensive study on the temperature effects on the PV module's output. In this graph, you can see the efficiency of a PV module over a calendar year as modeled using actual temperature and irradiance data for the Netherlands in 2012. It can be clearly seen how the efficiency is not constant but changing with the ambient conditions over the year. To give you an idea of the deviation from the expected efficiency, the rated efficiency is shown for this model. So you see, temperature effect cannot be underestimated as it can turn out to be the biggest reason for a low PV yield. The PV module considered here was a commercial polycrystalline module, and the module's parameters were taken from the manufacturer's datasheet. The difference between the expected PV yield with rated efficiency and the actual yield due to the temperature effect gives rise to a module ideality factor. This is nothing but the ratio of the expected PV yield actually available, taking into account the temperature effects. If the module ideality factor is 80%, that means that the module has lost 20% of its annual energy yield due to temperature effects. If the module ideality factor is 100%, that means the module is immune to temperature changes. Now, the extent to which the temperature impacts the module output is a function of the PV technology and the manufacturing process, which collectively decides the temperature coefficients of the PV module. The temperature effect is also a function of the ambient conditions. For the same technology, there could be a deviation in the temperature coefficients due to the manufacturing processes and other design modifications. The following graph shows the spread of a few of the common silicon-based modules based on their module ideality factors and the temperature coefficient. These numbers have been calculated after modeling the temperature effects of these PV modules for the ambient conditions in the Netherlands in the year 2012. The Sanyo HIT module shows the highest module ideality factor owing to its low temperature coefficients of power. More PV technologies are being analyzed at the Delft University to understand the extent of the temperature effects. As said before, the amorphous silicon technology show very low temperature coefficients due to their high open circuit voltage. This means they would show a better response under high temperatures. However, their efficiencies are far lower compared to some of the best crystalline silicon technologies. But conventional crystalline silicon modules are also very bulky. Polycrystalline silicon modules cover a lot of area. Monocrystalline modules are more area efficient but are more expensive. Amorphous silicon modules are cheaper, lighter and sometimes even flexible, but give poorer yields. So there is plenty of optimization to be done just for the choice of your ideal PV module for your system. The optimum choice will of course depend on the location, ambient conditions, the budget you have, among other factors. Fascinating, right? So this was a brief overview of the module level considerations. In the coming blocks, we shall look at more PV system components and concepts. See you in the next block. In this block, I will discuss the concept of maximum power point tracking, or as is commonly called MPPT. This concept is very unique to the field of PV systems, and this also brings about a very special application of power electronics in the field of photovoltaics. The concepts discussed in this block are equally valid for cells, modules and arrays, although maximum power point tracking concepts are usually employed at PV module array level in practice. For reasons discussed before, the solar cell has an IV curve as shown in the figure. As a quick recap, you might remember how the IV curve of a PV module is similar to that of a single solar cell, as the PV module is merely an interconnection of several solar cells. A series or parallel interconnection of cells increases the voltage or current respectively, but the overall nature of the IV curve remains the same. In similar manner, it can be said that the interconnection of the PV modules to form a PV array would yield comparable IV curves, albeit at different IV levels. Thus, it's reasonable to consider the IV curve of a solar module or array similar in nature to that of a solar cell. So let's head to the simple IV curve of a solar module. Now, the IV curve is nothing but the current voltage curve. This IV curve of a PV module is defined for a unique set of temperature and irradiance conditions. For instance, if the irradiance or illumination were to increase, the IV curve would also change to a higher level. In general, a higher irradiance gives a better IV curve, but a higher temperature gives a worse IV curve, and vice versa. Now, let's try to understand the concept of the operating point. At any given point in time, the solar module operates at a particular voltage and current. The point on the IV curve where the solar module operates is called the operating point. For a given irradiance and temperature, an operating point on the IV curve corresponds to a unique IV value. We know that power is voltage times current. If you draw the power voltage curve or the PV curve, it takes a form as shown. Of course, an operating point on the IV curve will also correspond to a unique operating point on the PV curve. Now, what is the significance of the P on the PV curve of a solar module? Well, this is the power that is produced and delivered to the rest of the PV system, and eventually the load. Therefore, it is clearly advantageous that the solar module operates at maximum power, as seen in the figure as the peak of the PV curve. Now, without any external electrical manipulation, the PV module's operating point is largely dictated by the electrical load seen by the PV module at its output. To get maximum power delivered by the PV module, it's therefore imperative to force the module to operate at the operating point corresponding to the maximum power, or as it's generally called, the maximum power point. This point corresponds to the peak of the PV curve or the knee of the IV curve. The simplest way to do this is to force the voltage of the PV module to be that at the maximum power point, or regulate the current to the right amount as that of the maximum power point using converters. But what if, after forcing the PV module to operate at maximum power point, the ambient conditions like irradiance or temperature change and in turn cause the IV PV curve to change as well? This would mean that the old MPP is no longer valid under these conditions. Thus, to be continuously at the maximum power point at all times, we would need to track any such changes in the IV curve and find out the new MPP. This process is called Maximum Power Point Tracking, or MPPT, and the devices that perform this process are called MPP trackers. So how do these MPPT devices work? An MPPT device is nothing but a hardware implementation of an MPPT algorithm or algorithms. There are several algorithms to track the MPP effectively. These are also called MPPT techniques. Some of the modern literature talks about two broad categories of MPPT techniques. Indirect MPP tracking, like fractional open circuit voltage method, or direct MPP tracking, like the Perturb and Observe method or the Incremental Conductance method. Each of these techniques have their own advantages and disadvantages. Let's talk about the indirect MPP tracking first. In this kind of tracking, simple assumptions and periodic estimations of the MPPT are made with easy measurements. An example from practice is the fixed voltage method. This technique is based on adjusting the operating voltage of the solar module only on a seasonal basis. This is under the assumption that the higher MPP voltages are expected during winter and lower MPP voltages are expected in the summer for the same level of irradiance. Of course, this method is not very accurate, and accuracy is increased if such an idea is implemented in a place with minimal irradiance fluctuations on a particular day. One of the most common MPPT techniques in indirect tracking category is the fractional open circuit voltage method. This method exploits the fact that a good approximation of VMPP is given by constant K multiplied by the open circuit voltage. This constant K for crystalline silicon is usually found to be around 0.7 to 0.8 in practice. In general, constant K is based on the PV technology and the kind of solar cells in use. How is this technique rationalized? Let's discuss that for a moment. We know that every illumination level and therefore irradiance level corresponds to a particular IV curve and therefore a specific level of open circuit voltage. It is found from practice that for a range of IV curves, the ratio of maximum power point voltage to open circuit voltage shows little variation. Thus, for changes in irradiance, if the open circuit voltage can be measured, the maximum power point voltage can be easily estimated as a fraction of the open circuit voltage. This technique is easier to implement compared to some of the more complicated techniques. What then are the drawbacks of such technique? Well, first, as the concept of K is just an approximation, this method does not always point us to the true maximum power point, but only in the region around the maximum power point, or as it's commonly called, the MPP region. Secondly, every time the system needs to respond to a change in illumination conditions, the maximum power point tracking algorithm needs to measure the open circuit voltage. How does the maximum power point tracking device measure the open circuit voltage of a solar module under operation? This is done by disconnecting the PV module from the load momentarily, or in other words, the PV current is zero so as to measure the open circuit voltage. Although temporarily, this results in a loss in production of the PV power. This handicap only worsens if this measurement of open circuit voltage has to be made more frequently. A slight modification to this method can help in overcoming this apparent drawback. This involves the inclusion of a pilot PV cell that is highly matched with the rest of the PV cells that constitute the PV module. The idea here is that the lone pilot PV cell receives the same illumination as the rest of the PV module, and a measurement of the pilot PV cell also gives an accurate representation of the PV module under consideration. Thus, while the PV cell provides for a good estimate of module's open circuit voltage, the maximum power point voltage can be calculated as the maximum power point voltage is equal to the K value times the open circuit voltage, and the PV voltage can be adjusted accordingly without having to disconnect the PV module. Note that the inclusion of PV cell merely avoids the losses due to module disconnection. This method would still suffer from the problem of depending on the K value for estimating the maximum power point voltage. Now, let's look at the more involved kind of maximum power point tracking, the direct maximum power point tracking. This kind of maximum power point tracking involves direct measurements of current, voltage, or power, and a more accurate, faster response than the indirect method. Due to time constraints, we shall look at a couple of the most popular kind of algorithms, which are sometimes also classified as hill climbing algorithms. We start first with the Perturb and the Observe or P&O algorithm. In this algorithm, a perturbation is provided to the PV module or array voltage. This would translate to an increase or decrease in power. If an increase in voltage leads to an increase in power, this means that the operating point is to the left of the maximum power point, and hence further voltage perturbation is required towards the right to reach the maximum power point. Conversely, if the increase in voltage leads to a decrease in power, this means that the current operating point is to the right of the maximum power point, and hence further voltage perturbation is required towards the left to reach the maximum power point. In this way, the algorithm converges towards the maximum power point over the several perturbations. You would have noticed that this algorithm takes advantage of the fact that the PV curve has an increasing nature to the left of the maximum power point and a decreasing nature to the right of the maximum power point. The problem with this algorithm is that the operating point is never steady at the maximum power point. It is always hovering around in the maximum power point region, although this could be minimized using very small perturbation steps around the maximum power point. This algorithm also struggles under rapidly changing illuminations. For example, if the illumination and therefore irradiance changes in between two sampling instants in the process of convergence, then the algorithm essentially fails in its convergence efforts. This situation is illustrated in the figure as well. In the latest perturbation, the algorithm has determined that the maximum power point lies to the right of point A, and hence the next step is a perturbation to converge towards the maximum power point accordingly. However, as the illumination changes rapidly before the next perturbation shifts the operating point to B, while the new maximum power point actually moves to the left of B. This can be severely erroneous because the algorithm has now reached a point B such that the power B is larger than power A. But the maximum power point still lies to the left of point B, which makes the algorithm think that the maximum power point is to the right of point B. This is detrimental to the speed of convergence of the P&O algorithm, which is one of the critical figures of merit in the field of the maximum power point tracking technique. Thus, drastic changes in weather conditions severely affect the algorithm's efficacy. Next, we look at another kind of direct maximum power tracking algorithm called the incremental conductance method. To better understand the algorithm, we shall first arrive at a relation between conductance and incremental conductance. Conductance of an electrical component is nothing but a ratio of current to voltage, or in other words, reciprocal of resistance. We know at the maximum power point, the slope of the PV curve is 0. dP dV is 0. Now, dP dV could be written as d, current times voltage, dV. Using basic differentiation, we get dP dV is current I plus the voltage times di dV. If the sampling steps are small enough, then di dV could be approximated to delta I delta V. Thus, at the maximum power point, delta I delta V is equal to minus I divided by V. To the left of the maximum power point on the PV curve, delta I divided by delta V is larger than minus I divided by V. And to the right of the maximum power point on the PV curve, delta I delta V is smaller than minus I divided by V. The algorithm exploits these basic facts about the IV and PV curve of a solar module. In general, the algorithm imposes a voltage on the PV module at every iteration, measures the incremental change in conductance, compares it with the instantaneous conductance, and decides if the operating point is to the left or to the right of the maximum power point. I will explain this in a brief conceptual flowchart. Note that this flowchart is not exhaustive. In this example, we see a maximum power point tracking algorithm based on incremental conductance method. The instantaneous voltage and current are the observable parameters, while the instantaneous voltage is also the controllable parameter. Voltage ref is the voltage value forced on the PV module by the maximum power point tracking device. It is the latest approximation of the maximum power point voltage. For any change in the operating point, the algorithm compares the instantaneous and incremental conductance values. If incremental conductance is more than the negative of the instantaneous conductance, this means the current operating point is to the left of the maximum power point. Consequently, the ref voltage is incremented. Conversely, if the incremental conductance is lower than the negative of the instantaneous conduction, the current operating point is to the left of the maximum power point and is decremented. This process iterates until the incremental conductance is the same as the negative of the instantaneous conductance, in which case the chosen reference voltage is equal to the maximum power point voltage. This maximum power point tracking algorithm can be more efficient at the maximum power point as it doesn't hover in the maximum power point region under steady state like the P&O algorithm. Also, low sampling intervals make it less susceptible to the changing illumination conditions. However, under very highly varying conditions and partial shading, the incremental conductance method might also be rendered less efficient. The main drawback of this algorithm is the complexity of its hardware implementation. It needs to not only measure the currents and voltages, but also calculate instantaneous and incremental conductance values. I will not go into the details of the hardware implementation of the maximum power point tracking techniques. It is beyond the scope of this course. Usually, a DC-DC converter is used for implementing the current or voltage regulation at the PV output. A typical example from power electronics is the buck boost DC-DC converter, like the one shown here. The algorithm needed to decide what voltage and current to force the PV output to could be any of the ones discussed here or several others from literature. The choice of the algorithm would dictate the complexity of the implementation. In modern PV systems, the function of the maximum power point tracking is often implemented within other system components like solar inverters and charge controllers like shown here. Please note that the list of techniques and typical implementation are definitely not exhaustive. In fact, several algorithms and implementation techniques exist in practice as well as in literature. There are scores of scientific papers, patents, and proprietary technologies existing in this rapidly growing space. In view of time, we have covered only the most common maximum power point tracking techniques. In summary, maximum power is delivered from the PV cell, module or array if the operating point is the same as that of the knee of the IV curve. An ideal maximum power point tracking device is not only able to track that the knee under varying conditions, but also maintain the voltage and current accordingly. In doing so, the device is expected to use as low an energy amount as possible so as to not undo the additional energy gains the maximum power point process provides. The maximum power point tracking device is also expected to respond swiftly and accurately to the changes in the ambient conditions that impact the PV output. In the next blocks this week, we shall look at the other components of the PV system that make the harnessed intermittent solar energy usable for various applications. See you in the next block. Welcome back. Now we come to an important power electronic device that makes the modern PV system widely usable. I'm talking about the solar inverter. To know what an inverter is, we must first understand its need in the PV system. All the discussions we have had so far on the PV electrical output in terms of current, voltage and power have all been DC in nature. What do I mean by DC? DC, or direct current, is the unidirectional flow of electric charge. DC is produced by power sources like batteries, solar cells, dynamos, etc. The term DC has broad enough to be used for any electric signal that is unidirectional. Thus, it is common to talk of quantities like DC voltage, power, and current. The symbol for DC power is this. AC, or alternating current, on the other hand, is the flow of electric charge such that it constantly reverses directions. The usual form of an AC power is a sine wave. The symbol for AC signal is this. As a thought, DC signals can be looked upon as a signal with zero frequency. So why do we need AC power? After a brief war of the currents in the 19th century, AC power was chosen as the standard for central power generation, transmission and distribution. Till this day, almost all national electric grids are based on AC. Almost all households have what are known as the AC mains sockets. Consequently, most household electric appliances expect to be fed AC power, even though sometimes the internal circuitry of the appliances might use DC. Nevertheless, the fact remains the solar power produced needs to be converted to an AC form, so that the solar power is more usable in the electricity framework we have today. How do we make this conversion from DC solar power to the easily usable AC power? We need a device which can simply convert a DC electric signal to an AC one. This device which can make this possible is an inverter. Given the time constraints, we will not go into the internal circuitry of the inverter, but we will talk about the features of the solar inverter and its application in the modern PV system. Now, inverters could be classified based on their size, mode of operation, or implementation topology. Here I will talk about the classification based on the mode of operation. Under this, the inverters can be classified into three broad categories: standalone inverters, grid-connected inverters, and bimodal inverters. Here, a typical off-grid or standalone PV system is shown. Consequently, the inverter is a standalone inverter. In this case, the PV system is standalone. The load can only depend on the PV system for power. So the inverter that supplies AC power to the load has to appear as a voltage source with a stable voltage and frequency, supplying power at 230 volts AC or 110 volts AC, or as is the voltage standard at the location. Here, a typical grid-connected PV system is shown. Consequently, the inverter is a grid-connected or grid-tied inverter. In this case, the PV system is grid-connected. The load can depend on the PV system as well as the grid for power. There is an exchange of power between the grid, the inverter, and the load. The inverter latches on the grid frequency and voltage. The inverter's main task is to only pump power into the grid. So the inverter that supplies AC power to the grid as a current source, while the role of the constant voltage source in the system is fulfilled by the grid. Here we see a hybrid system. These configurations are much rarer. The PV system is capable of functioning either as a standalone system with battery storage or as a grid-connected mode. The inverter plays a crucial role as it has the necessary hardware implementation to work in either modes based on the operating conditions. In a standalone mode, the grid is disconnected and the system might cater to some special backup loads with the inverter behaving as an AC voltage source. In the grid-connected mode, the inverter behaves as an AC current source. These bimodal inverters are usually more expensive and are used less often. Now, we already know the basic application of an inverter in the PV system: power conversion from DC to AC. Can the inverter perform any additional function? The answer is yes. And thanks to the advancements in the power electronics, it's common to have inverters that implement a maximum power point tracking mechanism before inverting the voltage, thus ensuring that the PV modules or arrays are operating at the maximum power point. Apart from the modes of operation, inverters are also classified on the basis of the implementation topology. There can be 4 different categories under this classification. Central inverters, which are usually around several kilowatt to 100 megawatt range. Module inverters or micro inverters, typically rated around 50 to 500 watts. String inverters, typically rated around 500 watts to a few kilowatts. A string is nothing but a number of PV modules connected in series. And finally, multi-string inverters, typically rated around 1 kilowatt to 10 kilowatt range. Let's start with the central inverter. This is the most traditional inverter topology in use. As seen in the figure, this is a simple implementation with one central inverter catering to all the PV modules in a PV system. While this inverter topology increases the ease of system design and implementation, it suffers from several drawbacks. In large systems, large amounts of DC power will be transferred over long cables to reach the central inverter. This increases DC wiring cost and also decreases safety, as DC fault currents are difficult to interrupt. A maximum power point tracker implementation inside the central inverter will only cater to the entire system as a whole. In the various modules, strings are mismatched, let's say due to partial shading. The overall system output is drastically reduced. Also, the system is usually designed for fixed power. There is little scope for extendability of the system if more strings and modules need to be added. Next, let's look at the microinverters or module level inverters. As the name suggests, each module has a dedicated inverter with a maximum power point tracker. Therefore, the topology is more resilient to partial shading effects as compared to the central inverter topology. Clearly, the microinverters provide the highest system flexibility, since extending the size of a system under this topology is far simpler. Furthermore, the DC wiring costs are greatly reduced. However, the investment and maintenance costs tend to increase, especially if the cost per watt peak are compared. Then we have the string inverter concept, which seeks to strike a balance between the module level inverter and the central inverter topologies. The string inverter topology is more resilient to mismatch than the central inverter because each string is independently operated at its maximum power point, thus guaranteeing a higher energy yield. String inverters are smaller than central inverters. However, the implementation is more complex than the module inverter. Also, the partial shading will have a greater influence over the string inverter topology than over the micro inverter topology. Finally, the multi-string inverters. This concept seeks to combine the higher energy yield of a string inverter with the lower costs of the central inverter. Each of the strings is pre-power processed using low power DC-DC converters. Each string has its own maximum power point tracker implemented alongside the DC-DC converter. All the converters are connected via a DC bus to the inverter and ultimately to the grid. With a certain power range, only a new string with a dedicated DC-DC converter has to be included to expand the system size. We now have an overview about the solar inverters and their topologies. Of course, the choice of your topology for implementation would depend entirely on the system needs, size, and your system's budget. But in general, while choosing an inverter for your PV system, what are the requirements from a good solar inverter? There are several characteristics expected from a good solar inverter. As every power processing step expands power itself, the solar inverters are expected to be as efficient as possible. This is because we wish to deliver maximum PV generated power to the load or the grid. Typical efficiencies are in the range of more than 95% at rated conditions. Depending on the topology, it is expected that the inverters have inbuilt maximum power point trackers. Grid-tied inverters are expected to have active islanding detection capabilities. Islanding refers to the situation in which the inverter in a grid-tied setup continues to power the system even though the power from the grid operator has been restricted. Due to safety issues, islanding needs to be prevented. Therefore, inverters are expected to detect and respond by immediately stopping from introducing power into the grid. This is also referred to as anti-islanding. Since in a lot of situations the solar inverters are exposed to ambient conditions, these must comply with the temperature and humidity conditions of the location. Since grid-tied inverters pump power into the grid, they are expected to maintain very high quality so as to not corrupt the power flow in the grid. Thus, inverters are expected to have very low harmonic content on the line currents. It is a work in progress to increase the lifespan of the inverter, the crucial power electronic device in the modern PV system. A good inverter will probably reach, under favorable conditions, around 10 to 12 years of lifetime. This is the bottleneck in the modern PV system's lifetime, especially considering the fact that the PV modules can last over 25 years. We have discussed in this block the need for a solar inverter and also the different types and topologies of inverter implementation. However, there is one more crucial aspect that I have not talked about so far. That is the inverter sizing. This would largely depend on the system and the load requirements and the size of the rest of the system. I will discuss the inverter sizing when we know more about the different types of PV systems next week. So, see you in the next block. Welcome back. In this block, I shall discuss a vital component of not only PV system, but also renewable energy systems in general. As we discussed in the solar fuels block, there is a great need for energy storage at both small and large scales to tackle the intermittency of renewable energy sources. In case of PV systems, the intermittency of the source is of two kinds. Diurnal fluctuations, the difference of irradiance during the 24-hour period, and the seasonal fluctuations, the difference of the irradiance across the summer and winter months. There are several technological options to fulfill the storage requirements. How do we make an optimal choice for the storage system? Let us go back to the Ragone plot again. For solar applications, depending on the scale of implementation, we need a high energy density and a reasonable high power density. We cannot use capacitors because of their very poor energy density. For short-term to medium-term storage, the most common kind of storage in use is of course the batteries. They have just the right energy density and power density to meet the daily storage demand in the PV system. Of course, the seasonal storage problem at large scales is yet to be solved convincingly. For now, batteries still seem to be the most reliable option for PV systems in the small to medium scale. The ease of implementation and efficiency of the batteries is still unbeatable when compared to other technologies like pumped hydro, compressed air energy storage, conversion to hydrogen, and converting back into electricity and others. I will therefore focus on the battery technology in this block as a viable storage option for PV systems. Batteries are electrochemical devices that convert chemical energy into electrical energy. They are mainly classified as primary or secondary batteries. Primary batteries irreversibly convert chemical energy into electrical energy. Examples include zinc-carbon batteries and the alkyne batteries. Secondary batteries, or as they are more commonly called, rechargeable batteries, reversibly convert chemical energy to electrical energy. That is, they can recharge when the chemical reaction is reversed using an overpotential. In other words, the excess electrical energy is stored in these secondary batteries in the form of chemical energy. Examples include lead-acid batteries and lithium-ion batteries. It is the secondary batteries that we are interested in to explore as a possible storage option. There are several kinds of secondary battery technologies available that could be used. For example, lead-acid batteries. These are the oldest and the most mature battery technology available till date. I will go deeper into this widely accepted PV storage option later. Another secondary battery type is nickel metal hydride and nickel cadmium batteries. Nickel metal hydride have a good energy density comparable to that of the lithium-ion batteries. But the nickel metal hydride batteries suffer from a high rate of self-discharge. Nickel cadmium batteries have much lower energy densities. Due to the environmental impact of cadmium, the sale of nickel cadmium batteries for consumer use is largely banned in the European Union. Further, nickel cadmium batteries suffer from what is called as memory effect. The batteries lose their usable energy capacity if they are repeatedly charged after only a partial discharge. These demerits make the nickel cadmium and the nickel metal hydrides unlikely candidates for storage in a PV system. Next, we go to the lithium-ion and lithium-ion polymer batteries. These are being heavily researched currently as storage alternatives in various applications. Their high energy density has already made them a favorite in lightweight storage applications. But for their cost and low maturity, they would have been instant favorites for storage in PV systems. Note that you shouldn't confuse lithium batteries with lithium-ion or lithium-ion polymer batteries. Lithium batteries are disposable primary batteries, while lithium-ion and lithium-ion polymer are secondary batteries. The last and the most upcoming category is that of the redox flow batteries. The two main storage options for PV storage, lead-acid and lithium-ion batteries, are similar in the sense that their electrodes undergo chemical conversion during charging and discharging. Therefore, the electrodes tend to degenerate with time, adding to the inevitable aging of the battery. Redox flow batteries are a very new technology which seem to combine the properties of both the batteries and the fuel cell. The different reactants only exchange ions in the form of electrolytes through a membrane in a cell. Thus, the cell reactions proceed without a physical mixing of the reactants. The chemical energy in a redox flow battery is stored in its two electrolytes, which can be maintained physically separate from each other. Redox flow batteries thus have a high life expectancy. Let's look at the Ragone plot specific to the typical batteries only. This is slightly different from the Ragone plot shown earlier, as this shows the comparison between the various batteries technologies in terms of gravimetric energy density and the volumetric energy density. Volumetric energy density is the amount of energy stored per volume of battery. The typical unit of measurement is watt-hours per liter. Higher the volumetric energy density, smaller the battery size. Gravimetric energy density is the amount of energy stored per mass of the battery. The typical unit of measurement is watt-hours per kilogram. Greater the gravimetric energy density, lighter the battery will be. As seen, lead acid shows the lowest volumetric and gravimetric energy densities among the batteries. Lithium-ion batteries show ideal material properties to make it an optimal storage choice. Redox flow batteries have shown a lot of promise in their research phase so far. However, redox flow batteries and lithium-ion technologies are still being heavily researched upon. Consequently, these technologies are also very expensive. Due to the unbeatable maturity and low cost of the lead-acid batteries, they are still the storage technology of choice in PV systems, despite their much lower energy density and extremely low cycle life. Let's look a little bit more closely at the lead-acid battery. Here, you see a typical construction of a lead-acid battery. As with most batteries, the lead-acid battery is composed of several individual cells, each of which have a nominal cell voltage of around 2 volts. Lead-acid batteries could have different types of assembly. When built as a block assembly, the individual cells share the housing and are interconnected internally. For instance, to get the popular lead-acid battery pack of 12 volts, 6 such cells have to be connected in series. As the battery name suggests, the electrolyte in this battery is made from dilute sulfuric acid, H2SO4. 2 plates of opposite polarity are inserted into the electrolyte solution, which acts as the electrodes. The electrodes contain grid-shaped lead carrier and the porous active material. It is the porous active material that acts as a sponge-like structure, providing sufficient surface area to help the electrochemical reaction. The active mass in the negative electrode is lead, and in the positive electrode is lead oxide. When electricity is drawn, electrons flow from the negative to the positive electrode through the external circuit, causing a chemical reaction between the plates and the electrolyte. This forward reaction also depletes the electrolyte, affecting its state of charge, or SOC. When the battery is recharged, the flow of electrons is reversed, as the external circuit doesn't have a load, but a source that has a higher voltage than the battery to enable the reverse reactions. In the PV systems, this source is nothing but the PV module or array providing clean solar power. Remember that the use of storage is more common in stand-alone PV systems, because there is no other source of power to support the PV array. The loads are at the mercy of the availability of the sun. In such a case, storage options like the battery can be very useful. As an example, a typical solar irradiance profile is shown during the day. You can also see the load demand, which is significant in the parts of the day where there is no sun. In a stand-alone system without storage, even though the sun has more than enough power during the day, the system fails to utilize this excess energy to power the loads when the solar power isn't enough. With the introduction of the battery storage in the PV system, the excess energy from the sun during the day can be stored in the battery. The battery can then be discharged during the periods of low solar irradiance, and thus the load demand can be met. To summarize, we have seen the different kinds of battery technologies and discussed why lead acid is the battery of choice for most current PV systems. I will talk in detail about the various battery parameters in the next block. We also see how managing the different battery parameters is a whole new optimization challenge on its own. See you in the next block. Welcome back. In this block, I will introduce you to the basic parameters of the battery. We will learn about the different battery ratings and parameters. So let's get started. I will first start with the voltage and capacity ratings of the battery. Every battery is rated with a certain voltage and capacity. The battery rated voltage is the nominal voltage at which the battery is supposed to operate. The so-called solar batteries or lead-acid grid plate batteries are usually rated at 12 volts, 24 volts or 48 volts. Of course, the battery system in your PV system can attain any voltage based on the interconnection of several batteries at the system level. The term capacity in the domain of batteries refers to the amount of charge that the battery can deliver at the rated voltage. The capacity is directly proportional to the amount of electrode material in the battery. This explains why a small cell has lesser capacity than a large cell based on the same chemistry, even though the open circuit voltage across the cell will be the same for both the cells. Thus, the voltage of the cell is more chemistry based, while the capacity is more based on the quantity of the active materials used. The unit for measuring the battery capacity is ampere hour or amp hour, denoted as AH. It's good to recollect from high school physics that amount of charge is usually measured in coulombs. As the electric current is defined as the rate of flow of electric charge, the charge can also be equivalently measured in ampere hour. Therefore, we can quantify charge in both coulombs or amp hours. But we will stick to the more convenient unit of amp hours for measuring the battery capacity. I will shortly explain the reason for this. We must not confuse the battery capacity with the energy capacity. Energy capacity of the battery, or any storage device for that matter, is the total amount of energy that the device can store. This is usually measured in watt-hours. How do we calculate the energy capacity of the battery, knowing the voltage and the battery capacity? The energy capacity is nothing but rated battery voltage in volts multiplied by battery capacity in amp hours, giving the total battery energy capacity in watt-hours. You must be wondering, what is the significance of amp hours as the unit of battery capacity? The unit itself gives us some important clues about the battery properties. If we take a brand new battery with a 10 amp hour capacity, it can theoretically deliver a 1 amp current for 10 hours at room temperature. Of course, in practice this is seldom the case due to several factors, as we will see later. We now come to another useful battery specification called the C rate. Let's first understand how the battery charges and discharges. As discussed in the previous video, the charging and discharging of the battery at the cell level is just the right kind of chemical reaction taking place. At an electric level, charging and discharging depend on the direction of current into and from the battery respectively. How does this relate to the battery capacity? This is where the C rate comes in. C rate is a measure of the rate of discharge of the battery relative to its capacity. The C rate number is nothing but the multiple of the current over the discharge current that the battery can sustain over 1 hour. For example, a C rate of 1 C for 10 amp hours capacity battery would correspond to a discharge current of 10 amperes over 1 hour. On the other hand, a C rate of 2 C for the same battery would correspond to a discharge current of 20 amperes over half an hour. Similarly, a C rate of 0.5 implies that a discharge current of 5 amps over 2 hours. In general, it can be said that a C rate of NC corresponds to the battery getting fully discharged in 1 over N of an hour, irrespective of the battery capacity. In general, a higher or lower C rate will depend on the charging and discharging current that the battery with a certain capacity experiences. Like every other component in the PV system, the efficiency of the storage system is also of high importance. In the last video, you saw how we selected battery from a host of other storage choices. We said that the batteries, apart from the ease of implementation, offer some of the highest efficiencies. Usually, for storage technologies, we talk about round-trip efficiencies. In simple terms, it is the ratio of total storage system input to the total storage system output. For example, if 10 kilowatt hours is pumped into the storage system while charging, and you can effectively retrieve only 8 kilowatt hours while discharging, then the round-trip efficiency of the storage system is 80%. The round-trip efficiency in case of the batteries can be broken down and studied further. The batteries are reported to have two kinds of efficiencies. Voltaic efficiency, it's the ratio of the average discharging voltage to the average charging voltage. This stems from the fact that the charging voltage is always a little above the rated voltage, so as to drive the reverse chemical reaction in the battery. Then we have the Coulombic efficiency. This is defined as the ratio of the total charge out of the battery to the total charge into the battery over a full charge cycle. Battery efficiency is defined as the product of these two efficiencies. This overall battery efficiency can be seen as the round-trip storage efficiency that is usually considered while comparing different storage devices. This battery efficiency includes the effects of all the chemical and electrical non-idealities occurring in the battery. Now, let's look at another important battery parameter, the state of charge, or the SOC. This is defined as the percentage of the battery capacity available for discharge. Thus, a 10 amp hours rated battery that has been drained by 2 amp hours is said to have a state of charge of 80%. Then we also have the depth of discharge, or DOD. Depth of discharge is defined as the percentage of the battery capacity that has been discharged. Thus, a 10 amp hours battery that has been drained by 2 amp hours has a depth of discharge of 20%. Thus, the depth of discharge and the state of charge can be seen as complementary to each other. Now we come to a very important parameter, the cycle lifetime of the battery. Cycle lifetime is defined as the number of charging and discharging cycles after which the battery capacity drops below 80% of the nominal value. Usually, the cycle life is specified as an absolute number, but it would be a gross generalization to say that the battery lifetime can be stated as a single number without any other specification. Why? It's because the various battery parameters discussed so far are related not only to each other, but are also dependent on temperature. Let us discuss this interesting interplay of the battery parameters. Now, the cycle life depends heavily on the depth of discharge until which those charge cycles last. Also, it depends on temperature. This can be seen in the graph shown here for a typical maintenance-free lead-acid solar battery. Clearly, the battery lasts longer under colder temperatures of operation. Furthermore, for a particular temperature, cycle lifetime depends non-linearly on the depth of discharge or DOD. The smaller the DOD, the higher the cycle life. However, such a higher cycle life would also mean that those additional cycles you gain can only help you for a smaller depth of discharge. Thus, it could be said that the battery will last longer if the average DOD could be reduced over its normal operation. Also, battery overheating should be strictly controlled. Overheating could occur due to overcharging and subsequent overvoltage of the lead-acid battery. We will learn more about voltage and charge control of the battery in the next video. While battery life is increased at lower temperatures, there is one more effect that needs to be considered. The temperature affects the battery capacity during regular use too. As seen from the graph, lower the temperature, lower the battery capacity. Higher the temperature, higher the battery capacity. This is because at high temperatures, the chemicals in the battery are more active, and therefore the chemical activity tends to increase the battery capacity. Conversely, the chemical activity is hampered at lower temperature. It might seem strange, but it's even possible to reach an above-rated capacity of the battery at high temperatures. However, such high temperatures are severely detrimental to the battery health. When we say that the battery has a limited cycle life, or that is permanently run out of use, what exactly happens to it? What is exactly this aging effect on the lead-acid battery? Let us briefly discuss this. Sulfation is one of the major causes of aging. Insufficient recharge after discharges cause sulfate crystals to grow, which cannot be completely transformed back into lead or lead oxide. Thus the battery slowly loses its active material mass and therefore its discharge capacity. Corrosion of lead grit at the electrode is another common aging mechanism. This leads to increased grit resistance due to high positive potentials. Another cause is the drying out of electrolyte. Gassing can occur at high charging voltages, resulting in loss of water. This should be replaced by timely addition of distilled water. Otherwise, it dries out and the battery no longer functions. Thus, the battery also suffers from a limited lifetime. The battery space is being researched exclusively. There are already maintenance-free lead-acid batteries for solar systems that exhibit very high lifetimes. Of course, there are also the high-end products and would therefore be more expensive. Now, we have seen how the battery user has to be very careful in optimally using the battery so as to gain the maximum out of this effective storage system. But how do we go about controlling the battery parameters? We will see this in the next block. Welcome back. Now we come to an important power electronic device that makes the battery storage in the modern PV system widely applicable. I'm talking about the charge controller. What is a charge controller and why do we need it? Note that the use of a charge controller is found in a PV system with battery usage. In most cases, this would mean a stand-alone PV system. In the previous video about the battery parameters, you have learned the importance of having the right amount of current and voltage being provided to the battery. You know that the battery is an electrochemical device which requires a small overpotential when it needs to charge. However, battery technologies have strict voltage limits required for their optimal functioning. Also, the amount of current sent to the battery by the PV array and the current being discharged away by the load have to be within required limits for proper functioning of the battery. You have also seen previously how a lead-acid battery responds poorly to overcharge and overdischarge. You also know how the PV array responds dynamically to ambient conditions like irradiance, temperature, and other factors like shading. Under such circumstances, a direct coupling between a PV array, battery, and load is far from healthy for the battery. This means that we need a device that can interface three-way between the PV system, the battery, and the load, and ensure that the electrical parameters around the battery are maintained within the battery manufacturer's specifications. This is where the charge controller comes in. The modern charge controller performs a multitude of functions. These functions can further be enhanced depending on the set of technologies the manufacturer wishes to integrate within the device. I will discuss the most basic functions here. When the sun is shining in peak summer, there is enough PV energy meeting the load. The excess energy is sent to the battery. But when the battery is fully charged and the PV array is still connected to the battery tends to overcharge. This brings about its own set of problems like gas formation in the lead-acid battery, capacity loss, and overheating, to name a few. The charge controller here plays a vital role by cutting off the PV power from overcharging the battery. Similarly, in severe winters, when low irradiance causes the load demand to be more than the supply power, the battery is heavily drawn. The battery under such conditions tends to be over-discharged, which weighs strongly on the battery life as discussed in the previous block. The charge controller under such a case prevents over-discharge by disconnecting the battery from the load. For optimal performance, the battery voltage has to be within specified limits. The charge controller can help in maintaining an allowed voltage range so as to ensure a healthy operation. Also, the PV array could have its maximum power point voltage at different levels based on the temperature and irradiance conditions. Therefore, the charge controller needs to do an appropriate voltage regulation to ensure the battery operates in the specified voltage range while the PV array functions at maximum power point. This means that the modern charge controller can, and often does, integrate a maximum power point tracker within its design. We have seen before how the battery has certain C rates defined. Higher the charge-discharge rates, the lower the coulombic efficiency of the battery will be. The optimal charge rates indicated by the manufacturer could be adhered to by manipulating the current flowing into the battery. With proper current regulation, the charge controller is also able to control the C rates. At the very least, the charge controller can impose the limits on the maximum allowable currents flowing into and from the battery. Without blocking diodes, it's even possible that when the PV array is producing a very low voltage, the battery can load the PV array, or in other words, the battery can try to forward bias the PV modules and make them consume the battery power. Traditionally, blocking diodes are used at the PV panel or string level to prevent the supposed back discharge of the battery through the PV array. This function is also easily integrated these days via the charge controller. I won't go into too much of the hardware details, but most charge controllers usually have either a shunt or a series kind of controller. In a series controller, the overcharging is prevented by cutting out the PV array until a particular voltage drop is detected, at which point the circuit is completed again. On the other hand, in a parallel or shunt controller, the overcharging is prevented by shorting the PV array. This means that the PV modules work on the short circuit mode and that no current flows into the battery. These topologies also ensure over-discharge protection using power switches for the load connection appropriately controlled by the charge controller's algorithm. We have seen in the previous block how the temperature plays a crucial role in the functioning of the battery. Not only does temperature affect the lifespan of the battery, but it also changes its electrical parameters significantly. How does the charge controller handle this situation? A good charge controller these days comes with an inbuilt temperature sensor. Therefore, it compensates for temperature fluctuations and dynamically decides how the electrical specifications like operating voltage change with temperature. It successfully keeps the battery operating in the desired range of voltages depending on the temperature. For this reason, the charge controller is usually kept in close proximity to the battery, so that the battery's operating temperature is close to that of the charge controller. In extreme cases, if the battery is heavily loaded, sustained high currents might heat up the battery, and the charge controller would expect a different battery operating temperature than the actual value. However, high-end charge controllers are being designed to also take into account the temperature effects due to high currents. This pace of developing application-specific power electronics for PV systems is evolving at a very high pace. Thus, the charge controller can go a long way in increasing the lifespan of the battery by ensuring a healthy battery operation under most conditions. The modern charge controller has become an indispensable part of the standalone PV system. Like any other component of the PV system, it is expected to have a very high efficiency. I have given you an overview of this very important power electronic device in this block. This week has been about knowing the various components of your PV system. In the next and the last week of the course, I would show you how these components come together and create different types of PV systems, and what are the basic things to be kept in mind before designing your PV systems. So see you in the last week.